Good morning. All right, so let's get started. I know some of you will be watching the recording, and I hope everybody is getting ready. Okay, so we did some kind of review. We had a review guide last week, didn't we? Let's see. Okay, it's probably at the end of the file. Right, so this is the review guide. Okay, so I hope everybody got this. There's much we didn't get to cover, but we have covered the majority of the material that you would need to move on and be successful. Okay, so I'm going to bring up this review guide that we have, and so we can. Well, if you guys have any questions, and I'll be happy to answer your questions. Hold on. Right. If you don't have any questions, and I will just go by this agenda, that which is from beginning to end. The definition definitely is very important. 6 mathematical principles that we see used permeating the entire course instead, as in fact, they permeate the entire mathematics, the entire field of mathematics. The concept, okay, the concept on notes, page number 2, right? So these are page number 1. Page 1 in notes, and these are in page number 2, and these are in page number 2 as well. So let me bring up the notes just to confirm that. And I believe that that is the case. Right, I could be wrong, yes. Okay, truth table. To me, these are basics. Okay, these are basics, very basics. You will be encountering these concepts over and over again. Okay, because at the beginning of calculus class, it's about, what is, they start with function, right? But function is such a huge category, right? So just talk about function. We started with basic functions, and we talk about the adding, subtracting, multiplying, dividing, x turning into bologna kind of situation. We have lots of functions, and we composite functions. When you talk about composition of functions, you can generate infinite number of different kinds of functions. We haven't even talked about implicit function. Implicit function is another category that we haven't get to talk about, but you will encounter more of those in your future classes. So if you like, we could just go over some of the questions in quiz number 1. Okay, with what we have done so far. Right, with what we've done so far. So let's look at quiz number 1. I think quiz number 1 is a good, well, first of all, this was not my origination. This is from the calculus textbook, right? The calculus textbook. The author of the calculus textbook put together these questions, and typically a lot of these are typical mistakes, okay? So after we have done the entire semester, so let's look at these mistakes and see it from a new perspective, okay? See it from a new perspective. So quiz number 1, right? Now, the first question, of course, we understand that's the false, right? We started with that, right? So if x is any real number, right? Then the square root of x squared is equals to x, okay? If you have any questions, please don't hesitate to stop me, okay? And because nobody is asking any questions, so that's why I'm just spearheading to some of the places we can review these important concepts, right? So please don't hesitate to ask. All right, so we know this is a false, right? We know this is a false, of course. This is a false, and this is a very common mistake, okay? Very common mistake. But during the semester, we have learned that the reason this is false, right, is because the domain of this function, we understand how this operates, right? We have x is the input, and we do the x squares. We do the x squares, right? And after we've done the x squares, and then we do the square root of x squared. So there's an order of operations embedded there, and the output is going to be, right? It's going to be absolute value of x, right? So with that, we understand this is the flow. We call it, this is the flow, right? We understand that flow. From that flow, of course, that's a flow of function, right? That's the flow of function. And the domain of this function, right? The domain of this function is what is the domain of this function? The domain of function is all real numbers. X is any real numbers, right here, it's specified, right? X is any real number, right? And the range, what is the range? Well, we're taking square root of a non-negative number. So the range would be, the range would be this whole thing is always going to be greater than or equal to 0, right? So we also encounter some other common mistakes, you know, other mistakes, okay? Other mistakes such as, right? Other mistakes such as, some people say, oh, this is equals to plus minus x. No, that is wrong. Okay, so we went over these, right? So there are a variety of other mistakes. And what is more, in its application, right, in this semester, in its application, we have seen other situations. For example, suppose you don't have x squared exactly. You have, you have something like x minus 1 squared. What would that be equal to? Right? So the x here turn into bologna, and that bologna is x minus 1. What would that be equals to? That's going to be the absolute value of x minus 1. Right? So there's a, if you put them together, if you string these together, the absolute value, the square root of x squared is equals to, the square root of x squared is equals to the absolute value of x. And later, right, it turned into piecewise functions. Which we are very familiar with, right? At the beginning, you enter your calculus class. Okay, at the beginning, you enter your calculus class. you're going to be encountering these questions. As I said, no calculus class can avoid teaching this. Okay, they all have to deal with this. So we have these pieces, right? So we have these pieces. So this piece, right, that will follow the narrative, right? Remember the narrative, right? There's a big if statement here, right? And the if, can you guys tell me the narrative about this expression? Right, of course, this is equals to. Do you guys remember the narrative? That narrative is very, very important. Okay, good morning, everyone. That narrative is very, very important. Verbalize it, okay? Then you say, oh, I got it when we were talking about this. And afterwards, sometimes I just feel a little confused a little bit. That happens to everybody. But you have to truly make sure you truly understand it. Okay, so what is that narrative? The absolute value of a non-negative number is the same as the number. So the absolute value of a non-negative number is the same as the number, right? So this branch is saying that a narrative, right? So that narrative, right? The absolute value of a non-negative number is the same as the number, right? It's the same as the number, the narrative. That's what it means. So when you see that expression, right, this whole class is about understanding. This whole class is about understanding. Okay, and the other branch, the absolute value of a negative number, right? So it's full of shorthand notation. The absolute value of a negative number, right? The absolute value of a negative number is its opposite. Is its opposite. Okay, so which is that's the opposite. That's what's opposite. Right. So you can see from the from here, if you start making this mistake, and you're gonna miss out a lot of the other stuff. And that's why this mistake could cost someone easily 20 points in calculus class. In this class, it could also cost you, of course, but it's going to cost you even more. And no calculus class can avoid this function. Okay, no calculus classes, anywhere you take, any country you go to, they can avoid this function. You have to deal with it. Okay, of course, we also talk about, you just have to make sure you fully understand this. Right, so we have addressed this piece, and we have lectures about this. If you have any questions, so please don't hesitate to get this. Just get to the bottom of it. Just get to the bottom of it. All right, I'm going through this, right? So this is about the statement. Okay, this is still the state. It's a statement. A statement says this is the same as X. We know that's false, and then we go on. We say, hey, this is the same, right? And this is a mistake. Okay, so let me put it here. This is the mistake. This is a mistake, okay? That's not true. Okay, that's a mistake. Now, just about this topics of absolute value, close to the end of the semester, what did we do? We made it into piecewise functions, right? We made it into piecewise functions, right? So we can, let's see if we will graph it. Yeah, I graphed it. 2 pieces. And there are many piecewise functions that in our exercises, right? There were many piecewise functions in our exercises. Okay, so that's the piecewise function. Once you're in calculus class, you understand why this function is so important. Why this function is so important. Right? So that's a piecewise function. So from this mistake, we addressed all of these issues related to it. right? The narrative is very, very important. Okay, I want to nail that into your mind with understanding, with mindfulness, right? With understanding and mindfulness. And of course, this is, after all, it's just a statement. Okay, this is, after all, just a statement. And from this statement, we have situation that we have discussed near the end of the semester, and then we say, hey, this X is going to turn into baloney. Baloney. What does that mean? What does that mean? It could be a very complicated situation. Okay, the omega itself could be more complicated, and how we turn into piecewise functions, right? So turn these complicated situation into pieces, and in time we have to adjust the, according to the functions, adjusting the domains and so on and so forth. So those are the exercise that we work with, right? We worked with. Now these are just a statement. These are all about just statement. So let's look at the if statement, right? Let's look at the if statement. The if statements that we were talking about, right? There's three major categories. If, right, the three major categories, three columns. There are three major categories. One is the absolute value from the symbol, right? So these are all if statement, right? They are all if statement. So if it's, say, less than 1, equals to 1, larger than 1, right? And we know that these will turn into, the X will turn into baloney as well, right? And 1 could turn into other numbers. Do you guys see this, the progression of how it turned into what, right? They all actually originated from the same place, originated from just absolute value. So these are the if statement, and we did a graph, and we have a variety of forms of showing solutions, right? Forgive me, I'm not going to go into details unless you really need me to do that, okay? So here, I'm just very briefly talk about, but brief to the point that you understand what I'm talking about, you know what to relate to, okay? Okay, brief enough that you understand what we're talking about. And these are the places we see so many common mistakes. We see so many mistakes. Why we see so many mistakes? Well, I think maybe lack of understanding or lack of exercise, for whatever reason. These mistakes are very, very common. I pointed out those mistakes throughout the semester, right? And these will turn into all of that, right? So baloney becomes, in these situations. So you can see how a simple question can revolve or evolve. Okay, how these simple questions could evolve, because once we talk about omega, it could represent anything complicated. Anything complicated, right? So we have addressed this issue, right? That's false, common mistake, false. And this is true, right? So this is at the heart of everything else. This is at the heart of everything else, including its evolving, because including its evolution. And of course, in the if statement, there are some special cases. So what are those special cases, right? We have addressed those special cases, right? Say, for example, if this is less than a negative number, right? Or this is is larger than a negative number, right? And all of these if statements right, equals to a negative number, right? So there are all these different cases you can think of and figure out, and you definitely have encountered them all. You have encountered them all. Okay, just those at a very basic level. So this is just the first question on quiz number 1. You see, it involves it's question that we have encountered throughout the semester, didn't we? Right? So you need to make those connections. You need to make those connections. And at the heart of this, at the heart of these studies is right here. This is the heart. This is the heart. The understanding of this piece is at the heart of it, because it would change. It will morph into a butterfly, which involve have different aspects, right? And we're just talking from the perspective of grammar, that there are 2 kinds of sentences, right? There could 2 kinds of sentences. One, it's just a statement. This is just a statement, and then it turns into if statement. We have another kind of structure of sentences. No, no more. Right? I promise you there are only 2 kinds of sentences in mathematics. Have I seen the third kind? No, I have not. In computer science, the same. Same. Okay, if you're heading that way, right? But anyway, so that's the first question. That was just the first question, right? Number 2, feel free to stop me anytime. This mistake, and of course, you know that's a mistake. Very common mistake, popular mistake, okay? It's a terrible mistake. And yet popular. But we know that mathematical truth doesn't, facts in mathematics, it's not accepted, so-called fact, it's not accepted just because it's popular, right? It's not, it doesn't go by popularity. If true, always true, false, once false, right? Mathematical truths are judged very simply. If true had always been true. So you certainly know the counterexamples, but from these topics, right? Because these kind of forms show up in all the time, okay? Here and there, throughout this semester, we have dealt with this like a perfect square. Remember perfect square, and sometime in the midst of you dealing with a trig function, suddenly you have a perfect square showing up, right? You have a perfect square showing up. So this form show up, it could be from left to right or right to left, right? So, and of course we know that this equals to p squared plus 2pq plus q squared. These forms is just one of those academic questions. They just keep showing up. They just keep showing up, including the minus case. Okay, that's a terrible mistake, and this is the truth. And people use different forms, different symbols. So it could be capital A, capital B. It could be, whatever symbol they use. And this form is very, very commonly used. Okay, very, very commonly used. So as we get to this, we'll have to address some of the special formula, right? So special formula. So these 2 are one of the special formula. Special formula. Probably I should use plural, right? Is that the right plural? These 2 are a special formula, often show up on expected or unexpected, right? And certainly this is special. These are special case. Okay, these are the special case on trinomials, right? This is a special case on trinomials. Why do I say this? Because they are. Okay, special case, the right-hand side, it could be easily as they are special case on trinomials, which make perfect square. If you factor them, it give you perfect square. And the other special formula is that p squared minus q squared. This kind of mistake should never show up in anyone who takes calculus class. I mean, it should not show up in anyone's work who has taken algebra. Okay, but yet we see these mistakes often in our calculus class. Okay, so but anyway, let's addressing these special formulas. So this is just p plus q, p minus q. That's conjugates, right? That's conjugates. Left to right, right to left, right? Left to right, right to left. When we were rationalizing numerator, remember? When we rationalizing the numerator, what did we use? We use this property, right? When we rationalize anything, numerator, denominator, you always use this property. We always use this property, didn't we? All the time, all the time. Multiply by 1 and so on and so forth. So I hope you don't. Okay, I know you will not make this mistake, and you should not be surprised that when you are in calculus class and one of your classmates is making that mistake. Okay, I certainly hope that's will never show up again. Okay, number 3, that's a true. Of course, in the domain. Okay, that's a true. That is a true. Of course, in domain. Right? So this is related to what function? This function. We're talking about making connections, right? This function. That's its domain. Right? Now, if we look at this property and we know this is true, are there other truths? So how about 3? Root 3. How about root 3, root 4? And this, of course, is true in the domain of root 3 function. So these are the connections we're making. What's the domain of a root 3 function?
All real numbers.
That's right. Wonderful. All real numbers. All real numbers. Very good. These two are representatives of even number roots, odd number roots. Even number roots, odd number roots. So in general, we have these. Nth root AB is equals to nth root of A multiply the nth root of B. But you have to take into consideration when n is even. So these two are representative. Remember, these are two representatives. Will you encounter them? Yes, you do. Right? We have tons of exercise in the notes about how to simplify root 2, root 3, combining like terms, and all of those basic, very, very basic essential skills. And true in domain of what? Whatever those nth root function is. So then there's a difference, right? There are differences depending on n is even or odd. If n is even, then x is larger than or equal to 0. If n is odd, it's any real number. X can be any real number. Right? Number 4, however. Okay, I'm gonna, after number 4, I think I'm gonna take your questions. Okay, I'm gonna pause and take your question, because if I keep talking like this, you won't be, you probably don't ask questions. This is yet another very common mistake. Okay, very common mistake. Okay, so I will put it, it's a terrible mistake. Okay, it's a terrible mistake. Okay, you can see each mistake at different layers is, and it reflected the misunderstanding, right? For example, this one, it's probably reflected the understanding from here, because if you think this is true, then of course this is true, right? But that is the false. So all these mistakes seem to be connected as well. Okay. So this is not a perfect square. This is not a perfect square. So this will be going back to what? To the mistake in number 2 and this mistake in number 1, right? So these are terrible mistakes. So let me pause just a second. Okay, I'm gonna just refill my cup. I'll be right back. Get your question ready. Okay, if you don't have questions, of course, I can always talk about something that I think will be helpful for you, but I do not want to take all the time. I want you to have your question answered. Okay, I'll be right back, just a second, okay? All right. Do you have any specific question? Because we have that, notes, which is over 100 pages, lots of stuff, lots of stuff. Anybody? Everybody? No? No questions? Okay. Do you want me to, I can continue, but you understand you can stop me anytime, right? You can stop me anytime. You might be looking at some other stuff and you have, and this other mistake, of course, is a common mistake. And I don't need to talk more about it. I think most of you guys understand what it is, right? So we have a C, and this is 1 plus T, right? So the C and this C reduced, but there's no C here, so you cannot reduce it. So this is another terrible mistake. Okay, this mistake reflects, this mistake reflected, this is actually an elementary algebra level mistake. Okay, elementary algebra mistake. So practice some more reducing, right? Number 6, this mistake is absolutely unforgivable. I don't know why we see this mistake. Okay. So this mistake, number 6, is terrible mistake. It's a terrible mistake. But this mistake reflects that the person is very weak in algebra. Okay, this mistake reflects that the person is very weak in algebra. Okay, I'm not judging the person, I'm judging, the person, what he or she knows, what doesn't know. So you need to practice with these. This is a terrible mistake, and I don't know why we saw this mistake. 7. Okay, just remember, be reminded that these are the mistakes are not something I discovered and reported to you. This is by a calculus textbook author. Okay, his book is popular, is used for the last several decades and translated into international languages. And he, by the way, did I tell you, he was the richest mathematician on earth, because all these royalties he earned and all these, he died. His name is the textbook. His textbook. James Stewart. He's a Canadian. He died very wealthy, and his, offspring is probably still collecting his royalties or something. Okay, so this author, he listed these mistakes. So it has a different level of context from just this class. Okay, so it says something to us. Okay, number 7, of course, is true. Okay, number 7, because we look at, because the majority of these questions, because these questions are false, so you may have the impression of maybe everything is false. Well, that's not so. Okay, that's not so. Okay, so next questions. Okay, so this is true. This is true. Okay, you guys have any questions about it's true? Okay, so sporadically, if you look at all the first 7 questions we covered, right? Number 3 is true. Number 7 is true, and the rest are all false. But those false connected to so many different other things. Okay. So let's look at some of the other issues. Okay, let's look at some of the other issues. Number 8, for example. Because when you're in calculus class, you start with to deal with functions, right? It says if f is a function, then f of s plus t is equals to f of s plus f of t. First, we have to understand this statement is a very, very general statement. Because at the beginning of the class, we're talking about function, right? What is a function? Every function in in table one is a basic one is a function. And compounding those functions, adding, subtracting, multiplying, dividing, composing, we generate numerous functions. I would say we can generate an infinite number of functions. So this statement is saying for all those infinite number of functions, and this is true. Okay, that's what it says. So this is saying it's true for quadratic, it's true for linear function, it's true for exponential, trig, and all the different compositions of them. That's true. That's how powerful this statement is. But unfortunately, it is a terrible mistake. It's a mistake. Because it is not always true. In mathematics, we say false once, false, right? So to judge this one, you have to first recognize the magnitude of the if statement. It encompasses all those functions we have seen, right? Then with that understanding, then the next thing you think will be, is it true? Then you start to think of some concrete questions. Because if this is true, what does that imply? Right? So sometimes I'm talking about how you judge, how you think about, because in a lot of situations, you have to make that judgment call yourself, right? You may not have a teacher next to you. You may not have a teacher next to you, or you may not, you have to trust your own judgment. So you first have to understand, what does this imply? So if this statement is true, because sometimes you think, oh, is this true or is it not true? Then you say, well, if this statement is true, what does that imply? Right? So you have to understand the operations of these functions. You have to understand the operation of functions, which we emphasize throughout the semester. How does this operate? You have input, right? So you have input S, input T. And then you're going to do S plus T, right? So input. So now we have, of course, multiple. And that's how the left-hand side operates. And the right-hand side, how does each one opposite? Well, f of x operates, right? So the input is S. Right? And then input to f of s, it produces f of s. And for t, the same thing. You just change to t. And then what we do? We add them up, right? S of f of s adding f of t. So let me set this up. Let me set this up in a certain way. Okay, so you can see better. Right, so you first have to understand what this is. Right, so that's what it is. So this is the input, and this piece, right? And the input here, the input is t. And then f of x, after you get the output from both, that's how you add them. So these are the differences in processing. Remember, throughout the semester, we keep talking about the flow of the function, right? The flow of the function. How does it flow? Right? So what does it say? That's what it means. For concrete function, okay? Because this statement is for any function, right? That's what it's saying. So then you naturally you'll be considering what if the function is, say, I'm going to give you an example. Absolute value of x. Will that be true? So what does that imply? So if the function in our consideration is this guy, what it implies, what does it imply? F of s plus t. What does that imply? Imply the absolute value, right? So this rule, it becomes that. Is that true? Is this true? We have addressed these things, right? These are in our exercise. This is a false. Okay, this is a false. So very soon, you're going to find that you have many functions that will make it false. Right? Let me give you a few. Okay, and this is all related to the common mistakes we talked about earlier. Right? If this is true, that implies that is true. And at this moment, you're gonna derive all these. You already have your counterexample. You already have your counterexample. So that's what it implies, right? That's false, we understand, right? So this statement, which is a bold statement, very general statement, it's false, completely false. Because a false once is false. We don't have to give you 2 examples, but the reason I give you multiple examples is because I want you to see the implication. If this statement were true, this mathematics, the entire field of mathematics will be turned upside down. Okay, so power 3 is not true, right? So this is, of course, is false as well. So at the heart of all of these, we really need to understand the notation. The notation. Okay. So throughout the semester, we talk about notation, we talk about flow. All the time, right? All the time. And where did that flow come from? Order of operation. Please excuse my dear Aunt Sally. That was at the heart of that. And when did we learn that? Long time ago. In computer programming, it's designed according to order of operation. Order of operation was designed into every program. You're talking about Python, you're talking about Fortran, which is very old language, C, C++ these days, all the programs in AI, order of operation. So you must understand the flow. The word flow is not used in mathematics usually. Okay, I bring it into mathematics, but in computer science design, there's something called flow chart. I was not only original in inventing those words, I just borrowed that word and into mathematics. All right. So this is a paramount mistake. This is a horrible mistake, right? But you can see how big that mistake is. That mistake is huge. That mistake is huge. Okay, it's a terrible mistake. So let me mark it. You see you see the magnitude, right? Okay, you see the magnitude of such a mistake. If I continue, I could continue because this continuation of this mistake, you will see that all the functions we have talked about, right? What's the implication? If the function we talk about is, say, e, that means e s plus t is equal to e to the power s plus e to the power t. If the function is e, right? And of course, we know this is a false. Do you guys see the magnitude of that mistake? It's an understatement that this is going to turn mathematics upside down. Then you say, well, you have all these mistakes that, all these terrible consequences of this mistake, right? This is a way of thinking. Sometimes, let me give you some more, okay? What if it's sine x? What does that imply? It implies that sine of s plus t is equal to sine of s plus sine of t. That's the implication. And we know that's not true, right? We know that's not true. And it could apply to all the trig functions. And let me give you just one more. Okay, I picked some representative. Okay, say log ln x. What's the implication of that? If that were true, that means ln s plus t is equals to ln s plus ln t. What am I doing here? Equals ln s plus ln t. Right? So this list can go on. Then you say, oh my God, that is a terrible mistake indeed. But if there is a situation, it is true. If there is a situation, it is true. And my answer is yes, there is a situation, it's true. But then you say, when is it true? Sure, all these other situations, and this statement is terrible, right? F is a function. We cannot use this. But can we make some adjustment to this statement so that it is true? The answer is yes, there is a situation, it is true. Do you want to know that? Because this will be related to something you're going to learn in linear algebra. If you guys are heading that way, so after your calculus series, you're going to learn linear algebra and a differential equation. And so if we change the word to linear function, it is true. right? I will show you why. I'll show you why. So what is a linear function? What is linear function? If your function has this form, mx plus b, it is true. Does this look familiar to you? Elementary algebra, line. Okay, you can even prove it, it's true. If you have a linear function, it is true. So you see, just a word difference, right? Just a word of difference. And of course, if it's a constant function, it is also true, right? If it's a linear or, and then, so this statement can be modified or it's included, okay? It's already including the constant, so I don't need to elaborate more, okay? So this will be something you might see, and I think most likely you are going to see in calculus class, in linear algebra class. In linear algebra class, this is actually an important truth, important fact. Okay. But if you remove that word linear, and this will be a terrible mistake, right? This is how mathematics is being examined word by word. Word by word. Okay, so the next one, number 9. Okay, I have addressed this in our practice, right? So I'm going to address this one more time. F of s equals to f of t, then s is the same as t. What does that imply? You first have to understand what it implies, right? You first have to understand what it implies. The output are the same. The output are the same, right? We've been talking about input output the entire semester. I want to nail that into your head. This tell you the output is the same. Does that mean the input are the same? Not always, right? Not always. In some cases it's yes, in some cases not. So one is true, one is, so in general, if you don't tell me the specifics about the function, then this is false. This is false. Okay, but one is true. Right, so these are the questions we're going to ask. That mathematics examine these questions, right? Can we judge from output about input? Can we draw a conclusion from output about input? Right, the definition of function saying, well, if the input are the same, of course the output is the same because the output is unique, has to be unique in the definition. But if the output is the same, does that imply the input are the same? And we have numerous examples, right? We at the time when we were talking about exponential function, logarithm function, we're solving those equations. We actually have used some of these facts, right? We have used some of these facts. So, for example, if you have e to the power of, okay, I'm using function which is very directly related to your calculus experience, and then would be experience, right? May not be exactly the same question. If this is true, then for sure S is the same as T. This is true. Why? Because e to the power x is a increasing function. Okay, so this is true. Right? Now, let me give you another situation. Could I say if sine s is equals to sine t, then s is t? Of course not, because sine is not an increasing function. It's up and down, right? It's up and down, and this will be false. And this will be false. Do you guys follow me? You guys have the example in your mind, right? Sine 0 is equal to sine pi, but 0 is not equals to pi, right? So when is it true then? So sometimes it's true, sometimes it's false. Then you're going to examine all these functions that what do they have in common when it's true, and what do they have in common when it's false, right? You see how logically we're thinking about these questions. So when is it true? If f is 1-to-1. Okay, you can see sine is not 1-to-1, right? Sine is not 1-to-1. So this piece is true conditionally. Okay, it is true conditionally. When it is 1-to-1. So 1-to-1 including, increasing. If increasing is 1-to-1, decreasing 1-to-1. Right? So you also think about the relationship between the concept we talk about in on page number 2. Function 1-to-1, increasing, decreasing, how they're related. Is increasing naturally 1-to-1, or is it 1-to-1 naturally increasing? You have to think about these questions, right? So what if anything, I think math just make us think a little deeper. But I promise you, okay, I promise you, I had some conversations with people who work in, local companies and stuff like that. A lot of the engineers, okay, I know some of you are heading to be engineers, software engineers, and so on and so forth. If you can make yourself a little bit stronger in mathematics, you will have a competitive edge at your workplace. That will translate into you might be, might be holding a more important positions. That does happen. That does happen. Okay, so if you make yourself be, stronger in mathematics, it comes with a lot of tangible or intangible benefits. And you can totally work on this on yourself. Okay, so what I show you here is just the thinking, the thoughts that go into it. The thoughts go into it. Just think a little bit deeper. Just think a little deeper. Okay, and this is something nobody can replace you. Okay, so I give you the conclusion, right? So right here, so number 10, right? It said if f is a function, then f of 3x is equals to 3 times f of x. True or false? Very big statement. This is a very big statement, right? Just like the one we talked about earlier. if f is a function. It's a huge statement, isn't it? All those, infinite number of functions we can make, you're telling me this is going to be true. And of course, this statement is going to be scrutinized very carefully. So before we can do that, I usually start with that. What does this imply? What does this statement imply? So what does this statement imply when you look at the statement in mathematics? Could be the gateway for further discovery. Okay, so you take the statement and you try to understand it. What does it imply? And maybe along the way, you might find something interesting. Okay, then the first question is, what does this imply? What does this imply? Because f is a function, so that tells you that if f is this function, one of the functions in basic one, is it true? F of 3x, that's true. But can you go on to say, oh, I got an example, it's true, therefore it's always true. Can we do that? Of course not. Because the mathematical truth is if true is always true, false once, false. Okay, so you have to continue that journey, right? You say, oh, how about I try x squared? And what does that mean? F of 3x will equals to what? 3x squared, right? 3 of fx is equals to 3 times x squared. Are they the same? This first one equals to 9x squared. Are they the same? That's false, right? So in the case of, that's true. And in the case of, that's false. False. That's how you examine. Do you see that's totally doable for every one of us? Right? It's false. But ultimately, it has something to do with the flow. Remember how much we emphasize the flow? We did the flow. What does that mean? So when people, this semester, I made a point to emphasize the usage of notation because I see that's the weak point of a lot of student entering calculus class. Okay, so let me input. Okay, and then 3 times, and then give it to that. And this other one, how it's being done is that input, and then f of x, oops, and then 3 times. Do you see the difference? So sometimes when our students don't understand the notation, they say, "Oh, 3 inside, 3 outside. What does that? What difference does it make?" Oh, it makes a huge difference. You follow me? Huge difference. And all these mistakes we saw and pointed out by this, richest mathematician in the world, right? At the heart is related to the understanding of the order of operation, as basic as that. Do you guys understand? So in the future, when you're taking calculus class, you have to make sure you understand every little notation you learn. You spend time on it. You say, what does this notation mean? Because you're going to learn a lot of new notation, right? In the South Bay, Los Angeles, when we talk about real estate, the realtor will tell you location, location, location. I'm not a realtor. I'm teaching mathematics. What I'm telling you is about notation, notation, notation. You need to understand the notation, because if you don't understand the notation, you don't go very far. So the notation I emphasize this semester, so the entire semester I emphasize is this notation. If you look back what I've done, I have that on top of my head. Okay. All right. So and of course you can go on with many examples, many examples. Okay. Number 11, number 12, those are definition of increasing function or decreasing function. So those are true. Okay, so those are definitions. Those are definitions. Okay, those are definitions of an increasing function. Okay, you're gonna learn that again. Okay, you're gonna review that in calculus class. Okay, and you're gonna be using them in chapter 4. Okay, decreasing function. But anyway, without further ado, do you guys have any questions you want to stop me? Because what I'm doing here is going to be what we're doing here right now. What I'm doing with you is very important for your future classes. For future classes, okay. And of course, we're laying the foundation for our future classes. But it's also a summary of what we've done in the semester. You know, you can see bits and pieces I put in throughout the semester. Okay, but at a different, from a different outlook. And number 13, of course, is false, right? So why number 13? When we do composition, decomposition, we already see this, right? Number 13. So if any one of you have a question, so please don't hesitate. I have the chat open in front of me. Just give me a shout, right? Just give me a shout. So number 13, what it says is that it says F composite G is G composite F. Is that true? Right? Then you first have to try to understand what does that imply, right? Because in this statement, there's no, it just tell you F and G are functions. It just tell you F and G are functions, right? It just give you a very simple statement. So it's a gigantic claim. F and G are functions. It's a huge claim, isn't it? Because we know that function include all of those infinite number of things we can create. And it just tells us that if we composite, right, we already know that this is not true. Remember, in the, I can point to you what exercise we talk about. Remember, we do decomposing. Remember, we do decomposing. Okay, so I'm going to use that example. If this is going to be related to your function of one is x squared, right? G of x. I'm sure you remember this example, right? Remember this one? And the difference between the two functions is one is the cosine square x, and the other one is cosine x squared. What a difference. Of course, there's a difference, and it will have consequential effect on the understanding of this. So this is the example, this exercise we've done in our classes. So let's try to see the general flow of that. How does this work, right? What does this mean? What is the composite G? Well, if you any function has to work on input, right? So this will be f of g of x. And the flow, so how does the flow go? The flow goes g of x. Okay. And then f of g of x. That's the flow. You follow me? How about G composite F? Work on input. That's G of F of X. And of course, you guys know the flow is what? You first do F of X, right? And then you have that G of F of X. You guys follow me? So I use a little bit simplified flow form from what we did in class. Can these two produce the same output? So this claim is saying for any input, okay, this claim is saying for any input, these two are always the same. In other words, you have two functions, you composite them in any order you want, different order, just two different order, right? You produce the same output. It cannot be true, right? It cannot be true. And you're going to see a lot of examples of like that, especially when you're in chapter 3, calculus 1, you're doing chain rule. You have to be aware of the order. I show you that technique, right? To peeling off. You will see the order is a crucial. You cannot switch any one of those orders, then you messed up. Okay. So in these circumstances, right? So how is cosine square x is made? So let's take this opportunity to review. How are these two composed given f and g here? Huh? What is it? Is it f composite g? Right? And this guy is what? Is G composite F. Are you guys following me? Right, we did those exercises. You can go back there to so are the end result the same? Of course not the same. Of course it's not the same, right? Right? Is it? It's not the same. Right, so in this concrete example, you're going to see a lot of these things here and there. So you have to be very clear about yourself. Okay. So this is the order. Okay, you square that. So furthermore, just to be reminded that this is the notation, right? And this other flow is what? This you have x, you square the x, right? and then you do the cosine x squared. Right? So they're different. They're different. So this is what? It's a false statement. And then the next question is, when is it true? When is it true? When f and g are the same, they're the true. When they're the same, when f and g are the same, that's the case, it's true. You can explore some more. Okay, so this is only, I don't know the how much studies on this. I would imagine very few, because it's not really necessary. It's the order matters a lot, right? In general, when f and g are the same, of course, they're the same. In other situations, you can always give counterexamples. You can always give counterexamples. So this is why this is not further studied. Okay, so this is true when f and g is the same. Okay, so I'm not going to elaborate on that too much. Okay, so let's move on further. It seems at times flying when we are having fun. Okay, number 14. Horrible mistake. Okay, horrible mistake. If f is a function, and this also says if f is a one-to-one function. Right? Then f of inverse is equals to 1 over f of x. Right? Terrible mistake. This shows completely no understanding of the notation. You can see from the domain's perspective. Domain, remember we talked about if f is one-to-one, one's domain is the other's range, right? So this will be addressing the domain for f is inverse, and this will be addressing a new function's domain though. This is not addressing f of x domain, because this has to include the denominator cannot be 0. And so you're telling me that these two have the same domain. Sometimes these two domains are not comparable. Typical mistakes that stem from this is that we see some of our students making this kind of mistake. This is one of the typical situation. Right? Still talking about the domain and range perspective will certainly kill this, right? But why does this mistake happen? Why does such a mistake happen? This mistake happens shows the student has totally little understanding of trigonometry in general. I hope you guys don't make this mistake. None of you should make this mistake. Okay, none of you should make this mistake. So I'll trace back to the notation, right? So what's the domain for arc sine? Sine inverse. So it's about ratio, right? The domain for arc sine, the x's are ratio. X will be treated as a ratio, and x is in this interval. X is treated as a ratio. How about this guy? The input, right? So let me go from another perspective, right? That shows the, well, of course, this is also opportunity for us to review, is that the ratio x which is in this interval, is the input, and give it to sine inverse, arc sine. It produces what? Angles. And this angle is between where? Negative pi over 2 to positive pi over 2. Okay, so that's about the left-hand side. How about the right-hand side? The right-hand side. What is the situation on the right-hand side? X, give the input to sine. And then reciprocal. What kind of input is qualified for X, for sine X? Angle. So even though they're both called X, their meanings are entirely different. Their meaning is determined by what? Determined by the function. So this X is a ratio. This X is an angle. And you take this angle, it produces a ratio. And then you reciprocal that ratio. And of course, here you have to emphasize sine X, right? Sine X cannot be 0. There's so much into this. You guys follow me? There's so much into this from our basic knowledge. Then as a result, X cannot be what? K pi. Right? We know how to solve that, equation, inequality. K is integer. Right? So this is what's involved. This expression, right? So you can see their domain is not even comparable. How do you compare ratio and angle? Do you guys follow me? And such examples is in the numerous. So understanding notation is paramount important. Okay, it's paramount. And next we enter the exponential logarithm piece, which we have addressed them. We have addressed them all. Since you guys are not asking any question, tomorrow please bring your questions. Okay, so we have 6 minutes left. So let me try to see if I can get as much as possible to you, right? 15, you can always divide by e to the power x. Yes, because what? Because e to the power x is positive. Remember that narrative we have? For any real number x. That's the range of e to the power x. Very useful stuff. We use it many, many times. Okay, so you can always divide by e to the power x. So that's true. Okay, and others are mistakes you have seen, right? 16, right? 16 says if a, well, let's look at 16. X 0 is less than a, less than b. Okay, is that true or not? True or false? Think about the ln x curve. It's true. Okay, it's an increasing function. ln x is an increasing function. Remember that curve? It always takes us back to the basics. Yeah, all of these questions always take us back to the basics. 17, right? If x is larger than 0, right? It's in the domain. Then is that true? This one demonstrates first of all, you want to look at the flow. You want to look at the flow. Okay. Please excuse my dear Aunt Sally. So what's the flow for this guy? And what's the flow for that guy? And secondly, are they the same? Okay. This is a false. This is a false. Why is it false? Because this notation and that notation are entirely different. You power the entire output versus you power the input. That's different. This latter one is equals to, which is the power. Okay, so these two are different. You follow me? And also, this actually also traces back. Okay, so this for this one you can apply the power rule. And the other thing is you can look at the flow, but you also can see that ln base this guy is ln x. We've done similar examples in our classes. Okay, 1, 2, 3, 4, 5, 6. That's what it means. And what does that mean? What does that mean? It means ln x. It means ln x plus ln x plus ln x plus ln x 6 times. Do you see the difference? 1, 2, 3, 4, 5, 6. Do you guys see that? And we have done an example in class. And what is it? It was in the section of solve inequalities, solve equations and inequalities. And the story goes like this. It's in an if statement. I think this was the exercise. Okay, you can go back. It's in the logarithm sections. It's in logarithm. We had done a similar example. Okay, at that time I emphasized these things. Okay, so whether it's 2 or 6, it doesn't matter. You just have to understand the flow. Okay, and the flow's perspective. Okay, so let's look at the flow's perspective. What I want to show you is really the basics is so important. Okay, so this guy's flow versus this guy's flow. Right, so these has 2 flows. And do you really understand the power? This is about understanding power, and this is also about understanding the flow, right? The input is x, right? You're going to do ln x, and then you're going to do the ln x power, right? And what about this flow? Is x, you give it to ln x, right? And then what? And then what? You do 6 times ln x. Are these two the same? That's to be examined. And this guy is equals to what? ln x to the power 6. We have such a power rule. We have such a power rule. Okay? In other words, this power rule tells us if x is given to as input, and then you're going to make this. All right? These two are the same. You multiply 6 times versus you do this. These two are the same. But not the same with this guy. You guys follow me? Right? So this is true. Okay, so these two you can do any way you want. Okay, so let me point it out. Okay, let me just clarify so you can take notes properly. Okay. So power rule says these two is the same. They produce the same output. You multiply by 6 after ln x versus you do x to the power 6 and ln x to the power 6. That's the same, but this is different. Okay, got it? There are these questions. There are 19 through 25. We will cover them tomorrow if we have time outside your questioning, your questions. Okay, because to me, this is a review and you certainly will see some bits and pieces of these in the final exam. Okay, so at the bottom of this is really the fundamentals, the basics. And once again, notation, notation, notation. Okay, as a student, all those many years ago, I knew I had to understand the notation before I can do anything. And you guys, my recommendation for you is you are going to encounter a lot more notations as you step into calculus class. Be sure you understand those notation before you do anything. Verbalize it, make sure you understand it, what it really means. Okay. So this kind of attitude and rigor is something you get yourself into. But the benefit, I think the benefit is going to be, will be, you know, the benefits you're going to experience will come year by year afterwards in your career. If you so choose to do a STEM career. All right. Without further ado, I'm heading to my office hours and I'm going to see you guys tomorrow. All right. Have a great day.
Thank you.
Thank you guys.